So, there is another class. So, we have to finish by 6:40 or something. Okay, I will take 10 minutes extra today, but okay. So, the next is field theory of RG I did. Now, let us compute the energy flux. That is also important quantity which I told you what is energy flux. Energy flux is energy coming out of the sphere of radius k naught. Okay. And it turns out we can do it using field theory, of course, to first order. So, there are approximations. I did not emphasize that, but let me I will tell you what is first order. Okay. So, you will just give me 1 minute, I will explain for this flux calculation. Okay. So, for shell model, of course, for I wrote the formula for the Navier-Stokes equation, which was in terms of velocity field u of, in fact, u of k dot, sorry, u p, no complex conjugate for this, k dot u q, and then I need to sum over imaginary part of this and sum over giver modes. The one which gives should be inside the sphere, right. This is inside, giver is inside the sphere, giver, and receiver must be outside the sphere, right. So, energy going from the modes inside the sphere to modes outside the sphere. Okay. So, we will get to that, that is my discussion after this flux calculation. Okay. So, I will not do the detailed calculation for Navier-Stokes, but I will show you how to go about doing it, I mean the sketch of the proof. But for the shell model, we can show, this is proven by various authors before. So, we have shell model, please recall that these are shells and I am at shell k n. So, we again look for the energy going out from the shells left of k n, and left of k n to modes to shells beyond k n. So, energy received by k n plus 1 class poo, but it is a local model, in the sense the interactions are only local. So, k n interacts only with 2 more shells in the right. So, we do not need k n plus 3, right, because k n can only interact maximum only up to k n plus 2. So, we stop there. Okay. So, there is no integral, there is just a sum, there are 2 terms. Okay. And the 2 terms are interaction of n minus 1 n and n plus 1, this is the term. Okay. The 2 of them are complex conjugate in Sabra model. So, there are 3 modes interacting, n minus 1 and n plus 1, there is a coefficient in front and there is imaginary part, this is imaginary part. Okay. And the next term is un plus 1, un plus 2. So, triad interaction, the three shells. So, this one is, so I mean you can put this stuff here, n plus 1, n plus 2, n minus 1. So, this one is n minus 1 and n plus 1, these 3 for the first term, and second is these 3. Now, okay, this one can be computed in numerical simulations. There is some analytical work, but you can easily do it in computer simulation. I simulate the shell model and by initial condition, this is initial value problem. Given initial condition, I can get un as function of time, all the uns, and then I can compute them. Okay, compute the flux, and it turns out flux is constant in numerical simulations. But let us try to see whether we get constant flux in the inertial range for using field theory, which is not RG. So, what I am going to do is not RG, but it is a field theory. So, first order perturbation. So, it will become clear when I write the diagram, and again I am going to do self consistent theory. That means, for the spectrum I am going to put Kolmogorov spectrum, and for the viscosity I am going to use that what I derived using field theory, okay, the RG. So, I am going to put that what I know the answer, and then I say, well, flux is constant, this goes self consistent. So, using the answer you show that that answer is consistent, it satisfies the equation. Okay. So, please recall that I force at large scale and there is a dissipation in small scale. If I do not force, there is no dissipation, then that is the equilibrium theory. Okay. In equilibrium theory, flux is 0. Okay. So, we need non-equilibrium, that means there should be there should be energy flow. Is constant or not, we do not know, but we will show that it is constant. Okay. So, this formula I had written before, and it is a very simple interpretation. So, if I take flux at two shells which are separated by slight distance dk. So, shell 1 and shell 2, two shells, and imagine the distance between them is dk. So, there is difference in flux. So, this is the term multiplied by dk, I can multiply by dk, right. So, that will be the difference in flux, right, that is a differential derivative. So, how can flux change? Flux can change in two ways. I inject energy into this cell, put in energy, which is Fk, by external force, not non-linearity, external force is required. Non-linearity, so non-linearity will not change it. Okay. So, that we know that non-linearity is giving you this fluxes, that is already taken into account. So, external force can change the flux, in fact it will increase pi k plus dk, right. If I inject energy, then the flux for the bigger radius will be larger, right, because I inject energy. But there is a dissipation as well, viscous dissipation, and viscous dissipation will act like a sink. So, if there is dissipation only, no injection, then the flux at a bigger radius will be lower, right. So, it comes with a negative sign. So, this is the dissipation and this is the injection by external force. But for the shell model, we assume that forcing it is at a very low wave number, small wave numbers, small cells, well small wave number cells. Okay. So, in the inertial range Fk is 0, here Fk is 0. So, this is gone. In the inertial range we can also assume that dissipation is weak. Why? Because your nu k squared E k is a dissipation rate 2. So, this k squared factor for small k, inertial range of k is not too large. So, then this is small. So, this is also gone. So, flux is to be constant, okay, that is what we want. So, let us compute the flux now. Okay. Now, so remember I had this interaction was un minus 1, un plus 1, 3 modes, right, 3 shells. If the prefactor the vortex is 2 a 3 k n minus 1, remember there is a vortex, there is a prefactor. Now, there are three of these arrows. So, they represent the velocity field. Now, let us assume this velocity field is Gaussian. So, what is the property of Gaussian variables? Odd, what about odd products? U, 0 non-zero. Odd, 3 of them, if you multiply, this was a mid-sem problem, you have multiplied 3 of them, what will I get? 0, right, because odd number of, well, I assume that velocity, the u's have 0 mean. So, all the odd ones will give you 0, but even ones you can write as a product, as a sum of 2 point correlation, that is this, well, all possible. Okay. So, well, I wrote same as u, then this will be factor 3, if same u, otherwise we have A B C D, then A B C D, A C B D, A D B C, 3 terms. Now, to first order or to 0th order, this is 0 if I do the averaging. So, flux is computed as an average, flux will fluctuate, right, this pi will fluctuate for different times, but we do average, in fact ensemble average. That means I have prepared a lot of shell models and I compute this flux at a given time, but they will give different numbers, different shell models, but then I have average. So, it looks 0, but then this is a problem, no, I mean I want non-zero flux, then what should I do? Say, well, that is where you make this Gaussian variable is quasi Gaussian, okay, and you say, well, I am going to go to the next order and I am going to expand this velocity field in terms of Green's function. Okay. So, I am going to have 3 velocity fields, so they are all expanded one at a time. So, if I expand this u n plus 1, this one, so the Green's function, and so remember in the last class, so the right hand side is 2 u's, right. So, it is going to be Green's function times 2 u's, correct. So, in fact, if you write this is g t minus t prime u t prime u t prime, okay, integral t prime goes from 0 to t. This is how it will be, I mean this property of the solution. So, u n plus 2 u n plus 1, sorry, this u n plus 1 will be this, where the prefactor in front, prefactor, and of course, the 3 u n's, but it turns out only one of them will give you non-zero values by this property that u n plus minus 1 should connect with u n minus 1 star, otherwise we have to get 0. Okay. This is exactly same as what I did for R g. So, u n plus 1, remember u n plus 1 had how many things? One term to the, both of them to the right, one is one in the left, one in the right, and one term is both in the left. Okay. So, what are the values here? U n plus 1 will be, both in the left will be u n and u n minus 1, right. Both left will be u n minus 1, one in the left, one in the right will be u n is in the left and u n plus 2 in the right, and third is both in the right. So, u n plus 1, u n plus 2, u n plus 3. Okay. Now, I am going to multiply this by these guys, right. So, which of the 3 terms will give you non-zero values? Will this guy give non-zero values? So, you will have u n plus 2, u n plus 3, okay. Then we will have u n star and u n minus 1 star. So, now these are Gaussian variables. Okay. Cauchy-Gaussian, I did it here, I mean I said this non-zero, I expanded it, but then I will say, well, now I got quadratic term, I will use Gaussian property for this use. Now, look, if I do this pair, what is it? 0, right. If I do this pair, what is this? u n plus 2 with u n is 0. If I next is what? U n plus 2, that and these two together. Choose any combination, you will get 0, because u n must be multiplied by u n star to get non-zero value. Shell n and shell n plus 1, if I multiply, I will get 0, because they are two different random variables, but if the same random variable with complex conjugate, I get 0 non-zero value. So, which is the term among the 3 will give you non-zero value? This multiplied by these two, because I have u n minus 1 here, this u n minus 1 multiplied by this, and this u n multiplied by that. So, only one of the 3 terms is giving you non-zero values, and these are here. So, this is u n star will give you this temporal correlation, 2-point correlation C n t minus t prime, and u n minus 1 will give you u n minus 1 t minus t prime. Okay. I hope this is clear. So, Feynman diagram basically just makes the calculation very simple. I do not need to write all this, I can just do it by drawing the diagrams. It is a prefactor, there is a prefactor, as I said, there is a vortex term, this is a vortex term. Okay. So, this coming from the first diagram, which is, well, this is the first diagram where I expanded u n plus 1, but as I said, I need to expand other terms as well, other fields as well. So, u n expansion will give you this Green's function and 2 correlation function. Okay, that is C n minus 1, C n plus 1, and third one is I expand u n plus 1 using Green's function, u n minus 1, sorry, u n minus 1, I get this. Okay. So, I have 3 Feynman diagrams and I know these values, they are one Green's function and 2 correlation functions. Okay. So, I will delete these guys, this is rough work now, and I am just going to, so I am going to just write down these formulas, equations for first term. Okay. First term, and these are the expressions. So, this is what, well, one of the terms I am looking at. Okay. So, there are 3 more Feynman diagrams for the second term. Flux has 2 terms, right, in the previous thing. So, first term I am doing this, but in that I am going to expand only n plus 1 is using Green's function. So, n plus 1 is Green's function, this one, and the 3 terms, but out of these only this guy is giving non-zero value, right, because that will connect with n, this one will connect with n, and n minus 1 will connect with that, and the prefactor will be I a 3 k n minus 1, which is here. Okay. So, I just substitute this u n plus 1, this u n plus 1 is substituted here. Okay. So, that will give me 2 correlation functions, this and that, and Green's functions. So, what is this integral? So, we get product of these two, these are okay, but I take the imaginary part. Okay. So, this is I sitting there, which is good, and I take imaginary, well, these are all real variables. Okay. For shell model, they are all real variables, but this I sitting there. So, I am take imaginary part. So, I get a 3 squared, a 3 here, a 3 here, k minus 1, k n minus 1. So, I get a 3 squared, k minus squared integral. Now, the Green's function is this. Okay, that is Green's function, and these are going to give me 2 correlation functions. Which one? This multiplied by that and this multiplied by this. Only one, there is no 3 terms, only one term, because other 2 terms are zeros. So, if I do that there, I will get, well, I need to also integrate. If I integrate the exponentials, I will get this term below, right. Integral of exponential will give the prefactor will come below, that this is one prefactor. From the 2 correlation functions, I will get these guys here, and the 2 correlation functions gives you give you this, and these are for unequal time, but unequal time correlation is written as product of equal time correlation, which is C n and C n minus 1. This is C n and this C n minus 1 above. So, this term is the value of this guy, this Feynman diagram, first Feynman diagram. Okay. And these are number, no, I mean a 3 is a number, k n minus 1 is a number, everything is a number, except we do not know what is C n and nu n minus 1, but I substitute Kolmogorov formula. Okay. And for nu n, what I derived with R g. So, that is what I will do. Okay. Now, this is one Feynman diagram, but I need to do it for 5 more. So, other 2 diagrams, this is from the same diagram I just reproduced. These 2 are I 3 and I 4, sorry, I 4 and I 5. So, I 1 and I 2 was for R g. So, I am using I 3, I 4, I 5 for these fluxes, and there is another diagram, right, another set of diagrams for the second term of flux. I am going to use that I 6, I 7, I 8. So, there are 6 integrals, 6 Feynman diagrams, okay, and denominator is this. They come from the time dependence part of Green's function and correlation function. Okay. Now, the other diagrams we just follow the same procedure what I just did. So, this is that n, n plus 1, n plus 2, second part of the flux formula, and just follow exactly same ideas. So, this is not square, this is pi n 2, the second term, which is this one, n plus 1, n plus 2, n. So, this is a prefactor vortex, and when I do the expansion I get this vortex and da 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 da. So, I 6, I 7, I 8. Okay. Now, I need to sum them up, right. So, there are 6 integrals. So, if I just add all the 6 integrals, I will get the flux. Okay. So, let us look at the total. This is that integral. Okay. So, remember the integral had correlation function, this correlation function, and below is nu n. So, let me just do it here actually, that is do I have space there? Well, let us do it here. So, the right hand side has C n plus 1, let us look at one of the terms, divide by nu n k n squared, okay, and there is a k n squared, right. So, I just look at this term. Now, what is the k dependence of this function, this part, this is k dependence, no. So, k n squared, these are C n is in shell model is k n minus 2 k n minus 2/3, not minus 5/3. Okay. I described that in the last class. I need to divide by k n to get the minus 5/3. This is k n plus 1, but this is a factor b will come. Okay. So, but this again k n minus 2/3, right. So, this is a numerator k dependence. Denominator k dependence, what is that denominator k dependence? So, nu n is k n minus 4/3 and the k squared I multiply, then I get k n 2/3. So, what is this k dependence? Constant, right. So, this 2 will cancel with 2 by 3 times 3. So, this is constant k to the power 0. So, this will happen for each of the terms. So, every term is constant in k. Okay. When I sum it up, I will get constant in k. Okay. But each of them will give some b factors. Okay. So, that is why you get these b formulas, k n plus 1, k n plus 2. So, all that will give you this b. So, numerator is function of b, denominator is function of b, and we get a number. But what is, how are we getting these? Okay, now let us go back again. So, two correlation functions. So, 2 spectrum will give you k Kolmogorov squared, right, and this viscosity nu n will give you what? Nu star square root of k Kolmogorov. There is a prefactor. If you recall, I said this square root k Kolmogorov was used to cancel things for R g, but it will sit there. So, overall what is the factor for Kolmogorov? K Kolmogorov 3/2 by nu star. So, this is a prefactor for the flux. So, that is what you get k Kolmogorov 3/2 by nu star. Okay. So, flux is constant. This is a proof that flux is constant by field theory, but I did to first order. I made these diagrams which are only to first order. We can do to higher order as well, but that will be too complicated diagrams, but that is how it is called first order perturbation. I expanded one of the legs using one Green's function, but for example, we had one Green's function and I connected like that, right. But then I could also expand this as a Green's function. So, I can do one Green's like that and two legs. Okay. So, this leg can connect with that, and so it is pretty complicated diagrams will come. So, 2 Green's function and more correlation functions. So, that I am not doing it here. Okay. So, flux is constant, but now we can, by the way, epsilon also will cancel. No? So, this should be this should have been cancelled. So, right hand side will get epsilon. There is a typo, there should be epsilon. Why? Go back. So, 2 correlation function will give what epsilon? Each of them is epsilon 2/3. So, they will give epsilon 4/3, right, epsilon 2/3 into epsilon 2/3. And what is nu n dependence of epsilon? So, nu n is velocity times length. So, velocity has epsilon dependence of epsilon 1/3. Okay. So, that will give you epsilon 1/3 below. So, this together will give you epsilon. Okay. So, this epsilon in the right which I had missed out. So, this epsilon will cancel with that. Okay. So, what do I get from this algebra? So, this object is a constant function of B of course. So, with that I can get k Kolmogorov 3/2 by nu star is equal to 1 by this whatever this constant is 1 by this constant. Nu star is known for a given B, nu star is around okay, I mean order 0.5. So, from this I can compute Kolmogorov constant, correct. So, that is how you compute Kolmogorov constant using field theory, and that is what. So, this is numerical simulation that flux is indeed constant and which matches with the field theory prediction. Okay. And I can compute Kolmogorov constant by same method for different B's, and Kolmogorov constant for is basically according to theory it is around 1.7, this number is around 1.7, this is 1 and this is 2. So, it is around 1.7. Of course, for small k, a small b, this b prefactor, well b is the ratio of k n plus 1 by k n is b. Okay. So, it depends on b, but okay, they are between 2 point something to 1.7 or 1.6. Okay. But if I do numerical summation, then my numbers are consistently lower. The numbers are around 1 or around 0.95 something, around 1. So, this is something which is not clear. Of course, there are assumptions made in field theory, but the numerical summation is I expect it to be more reliable. Okay. In field theory we made some assumptions and these assumptions are probably not correct, not all of them, and so this 1.7 in cell model is Kolmogorov constant is order 1. Okay. So, the factor of 1.6 between the two. So, this is how we compute Kolmogorov constant. Now, these are all non-equilibrium solutions, but they are equilibrium solution, in fact which is quite straightforward. So, the idea is that if I start with random initial condition for the shell model, then we checked numerically that it remains random. So, this correlation for any un star, okay, un plus 1, they are all, well anyway this should be 0, but even the triple correlation, this guy is also 0, identically 0. Look, for the non-zero shell, well I mean if I compute this for non-equilibrium shell model, when I force at large scale and decay at large small scale, this is not 0. We saw in our simulation, this is not 0, this one. But if I start with random initial condition, I get flux to be 0. This is that nu equal to 0 Euler equation, well Euler equivalent, not Euler equivalent, flux is 0 for equilibrium solution. So, it turns out for Euler equation, for Euler equivalent, these guys give you 0. So, flux is 0, and it is possible because un are all delta correlated, they are all white noise basically. So, even triple correlate they remain Gaussian, okay, they remain Gaussian, they are not quasi Gaussian. So, this comes in turbulence theory quite often, that the variable u's are not Gaussian, in equilibrium theories u's are Gaussian. So, they become non-Gaussian and there are deviation from the Gaussian, and that gives you flux. If they remain Gaussian, then you will get 0 flux. Okay. So, this is a very important contrast for the flux. Okay. So, detailed balance is respected, this is equilibrium solution, this is exactly same as thermodynamics. So, given shell model, it is not that it will always give non-equilibrium solution, for some parameters it gives equilibrium solution. Okay. So, now let us summarize. So, first order self consistent computation of energy flux, okay, computation has come twice. Okay. we did that and we get non-zero values. When I force at large scale and dissipation at small scale, constant energy flux, you can compute Kolmogorov constant by this procedure which I outlined, and the number is around 1.7 by theory. For equilibrium solution, the energy flux is 0. Okay. So, this is basically coming from the flux calculation, which is not RG. Now, let us summarize the field theory application to two shell model. So, non-equilibrium theory, right, when I have non-zero flux, a correlation function differs from Green's function, right. We saw that in our computation. Both of them have similar form for time dependence, but one of them was correlation function was this, but Green's function was simply this. So, there is a big guy sitting there Cn, okay. And of course, these are time dependent. When I was doing equilibrium theory, there was no time dependence. Okay. So, that is a there is a major difference. If you recall, our correlation our Green's function and correlation functions for 5-4 theory was this, at least a free Green's function. But if I G naught of k, but if I do include all the terms, then this m is changed, but Green's function is basically argue that m is modified, but it is of the same form. Okay. So, you can see the Green's function is very different. I hope you remember this one after the course. They are time dependent, and if I decay with this decay rate, viscosity we found this, which is changing with time. Energy flux is constant. We compute the Kolmogorov constant in the field theory. Theoretical predictions are close to numerical results, except Kolmogorov constant. But it turns out if I do Navier-Stokes equation, I get pretty much same convergence. Shell model has this Kolmogorov constant is lower than DNS. That means lower than what we get for Navier-Stokes. Okay, two more things. Coupling constant remains coupling constant. Well, I should use better English. Is unchanged under RG, and that is due to symmetry. And equilibrium solution is 0 flux, and this nu n is not altered; it remains constant.